Yeah. Hi, everyone. I hope you're well. Thank you for joining us today. My name is Yuri Moroz. I'm VP of Sales and Marketing at Enamine. And today I'm going to present something that maybe not really fit with Enamine. And we'll be talking about metal organic frameworks and their covalent analogs. But before we begin, I would like to do a few announcements. The webinar will be recorded, and you'll be able to access it afterwards on our YouTube channel. You are in a listen-only mode. So if you want to have, if you have any questions, please use the Q&A box to type them in. So we basically announce them at the end of the webinar. Let me introduce to you Maxim Seredyuk, a Doctor of Sciences and a researcher at the University of Kiev, who will be presenting today. Maxim is a scientific advisor at Enamine and an expert in metal organic frameworks. Maxim, yeah, please, the stage is yours.
Thank you very much. Do you hear me?
Yes, we can hear you.
Yes, okay. So yes, hello everyone. So I'm going to talk today about linkers for metal organic frameworks and covalent organic frameworks. In this talk, we will see a brief overview of the classical examples from scientific literature on the topic with some recent examples of the real world application. So we will learn what is porosity, what are the MOFs, synthesis of MOFs, geometry of metal nodes and linkers. We will see examples of the organic linkers and their types. We will check the periodic table of reticular chemistry strictly related to the MOFs and COFs. Also, we will design an organic ligand to vary the pore size. We will check the functional purpose of the metal organic frameworks. Also, there will be a few words about the congeners of the MOFs, COFs, covalent organic frameworks, and we will check also how active this area of the scientific researchers. So let's start. First of all, MOFs, metal organic frameworks, conceptually are very close to the porous materials. The porous materials are ubiquitous in our lives. A few examples in nature are shown on the slide. These are organism tissues, bones, different plants, parts of insects, eggshells, and different minerals. Also, there are plenty of artificial porous materials, which we intentionally or unintentionally use in our life. For example, bread, or for example, construction materials. They all are porous, ceramics, piece of chalk, and of course, the activated carbon. According to the International Union of Pure and Applied Chemistry, UPAC, porous material consists of regular organic or inorganic structure supporting a periodic porous system. We can tell also that porous material exhibit permanent porosity and a specific surface area, because since we have voids, we have walls, and these walls have some area. Porous material is the size of pores, which can be micro, meso, or micro pores, depending on the size. Natural porous materials mostly have irregular structure of pores, while artificial materials are highly organized. Examples of porous materials, artificial or semi-artificial, that's activated carbon, zeolites, microporous polymers, metal organic frameworks, and covalent organic frameworks. So let's have a look on two examples of well-known porous materials, that's activated carbon and silica gel particles. Both are characterized by disordered structure, which depend on the method of preparation, and simultaneous presence of different size of pores. If we just look on the cross-section of the activated carbon particle, we will see that the structure is a bit chaotic. It's not organized, but there are islands of graphite-like structures or graphene-like structures. while the rest has no definite structure, cannot be described. Specific surface of the activated carbon, that's the surface of all surfaces, inner and outer. That can be up to 800 square meters per gram. For example, for the highly organized graphene sheet layer, that's just one layer of a graphite, just to remind you. It has area of 2,600 square meters per gram. Silica gel particle can be characterized also by pores of different size. There are meso, micro, and macro pores. Let's talk about metal organic frameworks. That's an artificial class of hybrid organic and inorganic compounds. Essentially, these are coordination compounds. That's coordination polymers formed by inorganic metal ions and organic molecules. Initially, it was discovered by chance, maybe even. It's a curious type of the coordination polymer. But over years, due to very high activity in this area, this topic became one of the top topics, top research areas in chemical science, and finally found its application for gas storage, separation, catalysis, and so on. Because of the very fast development and since a lot of examples were accumulated, Omar Yaghi, that's one of the founders of this topic, coined a term, reticular chemistry, for this particular kind of chemistry. So what are MOFs? MOFs are self-assembled out of building blocks, metal ions, clusters with organic bridging ligands. They are well known for their structure, permanent porosity, and tunable structure and physical properties. Here are just a few examples of different topologies of the already classical metal organic frameworks with different metals and different ligands. Let's have a look how we can synthesize a MOF. All chemists like simple chemistry. So when by mixing reagents in some solvent, the final product is easily obtained, and in crystalline form. And this is namely what happens by the synthesis of MOFs. So you take a metal, a linker, dissolve in some suitable solvent, heat it up, the obtained solution, and leave the solution for some time and maybe cool it down. And in a day or two, you observe formation of crystals. That's, let's say, an idealized way of the crystallization, of the obtaining of the MOFs, but in principle, it works in this way. So here it is important to emphasize that we have to look on the structure of the organic linker. It should be a rigid molecule, bridging molecule, so it should connect to two different metal ions or metal clusters. A three-dimensional network is obtained. It could be two-dimensional or one-dimensional, but this all depends on the nature of the organic linker. So in this way, we can combine many different metal ions and organic linkers. For convenience, linkers and metal ions, metal clusters are visualized in the form of geometric bodies, which are interconnected, and so the topology can be easily identified. Let's have an example of that. So this is a classical already MOF5. It is formed by the clusters of zinc ions, that's so-called basic zinc acetate. It is formed in situ by the reaction of zinc ions with the decarboxylic acid, terephthalic acid. The reaction is very simple. So you obtain very well-formed crystals. If the structure is checked, then it has cubic symmetry. It is porous. There are two types of pores, one larger, one porous, one cavities. A type of cavity is larger, another smaller, and they're connected by the windows. So the crystal in principle is transparent in all directions for some gas, which is not absorbed, and can be represented in the form of this cube. There are other examples. There are a few. As linkers can be used at any bridging ligand, so it can be some decarboxylic acid, furan decarboxylic, pyrrolidine decarboxylic, tetracarboxylic, diazo compound, tricarboxylic, and so on. And even nitrogen-containing compounds, the only requirement, they should act as linkers, so they should connect to metal ions in between. Practically all metal ions known from the periodic table can be used as the metal linkers. They are used as by itself as cations, or they can form more complicated entities, like we have seen the basic zinc acetate or other, where the hydroxy or oxygen is also works as a coligand. Examples of linkers. There are plenty of linkers synthesized up to now. The investigations, the researches were started from very simple compounds, commercial compounds available at that time, but eventually the researchers tuned to more complicated entities. For example, more complicated ligands, linkers. You can see that here examples which are pretty complicated and require a lot of skills to prepare them, especially maybe three-dimensional and so on. Up to now, a large array of the data was collected. So it was developed a periodic table of reticular chemistry. So if we combine different geometries of one building block and another, we can predict to some extent the topology of the formed final network. So this can be used as a guide, but there are still some gaps. There are some unknown compounds, whether it's impossible to get them or they're just there are no examples prepared as of today. Let's make an experiment. So the table says that it doesn't matter what's the chemical nature of the linker. Important is the geometry. Let's check it. This works, in fact. It's called isoreticular expansion. So we take a ligand, we extend the size of the cavities formed by the final MOF, but we keep the geometry, the topology of the crystals. So it works very well. Let's change a bit the ligand. So we take the same one, the same topology, not the same. We introduce additional carboxy group. So we get the hexa carboxylic acid. We change also the metal. We, in principle, obtain what is expected, but this particular case is important to talk about because it shows just a huge specific area. That's 7,100. Remember, activated carbon is just 800 square meters. So this is almost 10 times more than that. How much is that? Let's compare with something feasible. Here we have a very nice Olympic stadium just at the center. It's a modern built a bit more than 10 years ago. Its football field is built according to the current standards. According to the Google Maps, the dimensions from gate to gate, that's 110 meters, and the width of the field is 70 meters. So in total, that's 7,700 square meters. That's practically comparable. But look, this is the surface of 1 gram of the compound. Another example of the isoreticular substitution. Let's take another compound. This is well-known compound. It's serious, call it IR MOF74. It is important because here we can easily modify the ligand. We can increase the number of the phenyl rings which are in this ligand, and in that way very clearly modify the size of the channels running across one of the directions of the crystals. The final member of the family has 11 benzene rings in the ligand, so the pores are so large that they can be even seen under electron microscope, and in principle confirm the data which we know from the structural X-ray diffraction method. The synthetic route is pretty simple. Remember, we need rigid ligands. So here the chemistry is somehow restricted to those functional groups which form very straightforward, or at least predictable linkers of the linkers. So in this case, that's we can sequentially increase the number of the benzene ring and obtain the ligand with 11 benzene rings, and for that is used technique, but nonetheless quite laborious. So we know how to use the metal ions, linkers, solvents, and so on. We know how to synthesize. We created MOFs, but here appears the question: what for are these MOFs? What for we synthesize them? And there are answers to this question. There are pretty a lot of application, scientific as well as real life application. Let's check that. So the first example I want to talk about is gas absorption and separation. This is an actual problem because the methane, the natural gas, is widely used everywhere in the energetic industry, and even in the householding it is used as an energy source. So it is important to store it and to transport it. And to store it, it requires large, very high pressure to store it in a small volume. So for that we need high compression to store in some volume, or extreme reduction of temperature. These two different processes, CNG and LNG. But there is also an alternative way to store it. That's called absorbed natural gas process, ANG. So with the same vessel, but load it's first with some material which can absorb the methane. So let's have a look. The first example I want to talk about, that's the MOF based on the ligand bitriazole, pyrazole. It can be deprotonated, and with cobalt it forms a network which is in the dissolvated form is collapsed. But when it absorbs some methane, the pores are become opened, and a lot of gas actually is absorbed. So if you see the isotherms of the absorption, that's at room temperature, I guess. Yes, it's at room temperature. So at 350 bar, for example, here's the line. It can absorb up to 150 volumes of the methane per one volume of the MOF. We can play a bit with the metals. For example, we can substitute cobalt by iron, and we see a change in the isotherm. For example, this steep part is shifted to the higher pressure. But here also the organic part can be varied. So we can substitute, let's not disturb too much the system. Let's substitute hydrogen by fluorine, which has the same radius and the same distance, carbon fluorine. So in that way, we can modify also the absorption properties of the sorbent, and in that way we can shift the steep part of the isotherm to lower pressure, and in that way make it more useful, because we then need less pressure to saturate the material. And other examples of the gas absorption, there are a lot, because this topic was like one of the top subtopic of the MOF chemistry. So there are two MOFs. One called MOF 519, another MOF 520. The MOF 19, that one is shows record results, at least in this plot. So it can also absorb at 350 bar up to 150 volumes per one volume of the absorbent. Just compare, if you compress the gas, you get just 35 volumes. Of course, at 35 atmospheres, you get 35 times the gas. So, but again, the question, what about organic chemistry? Can it help to improve the absorption capabilities? And the answer, of course. We change with the system. This new system is based on the atrazine-based tetracarboxylic acid. Initially, in this initial unsubstituted, unmodified state, it shows the working capacity 140 cubic centimeters, the capacity. But eventually, by modifying, by slimming the ligand, polarizing and extending polarized ligand, we can improve this value almost by 30% up to 202 cubic centimeters. So thanks to the organic chemistry that can be improved a lot. Another type of the application I want to talk about, that the catalysis. Catalysis heterogeneous catalysis. So when the catalyst is the solid phase and all other reagents in the gaseous or liquid phase, there are conceptually two different approaches to build catalytic MOFs. One is to use catalytic metals to construct the framework. So the catalytic metal are used as a building block. They connect ligands or maybe somehow inside the ligand, and in that way they are used as the catalytic entities, units. And another way is to modify the ligand. First, we obtain a robust MOF, and then we modify it somehow, and in that way obtain catalyst. So let's check both ways. The first one is represented by the porphyritic system. It is cobalt-based porphyrin. It is obtained very easily. Just tetracarboxylic acid is mixed with cobalt, and in situ is formed the cobalt cluster, and the porphyrin is also metallated. So we obtain two-dimensional compound. But nonetheless, despite its two-dimensional, it has voids, and for example, can absorb gases, and later we will see it can also catalyze reactions. And then we modify a bit the ligand. We introduce the second carboxylic group. We obtain octacarboxylic acid. We use again the cobalt. Due to the effect of the substitution, we a bit change the way the cobalt is forming cluster. It forms another cluster. And in this case, we observe formation of the cavities. That's the porous compound with 1,400 square meters per gram at the specific surface. But we modify it more. We substitute one of the two groups on both sides. We substitute with another one bulky group, which oriented perpendicular to the plane of the porphyrin ring, and in that way we obtain another compound with cavities, with a smaller volume, specific volume, but with excellent catalytic activities. So if we check the oxidation of the epoxidation of transstilben catalyzed by the three compounds, we see that this, the last one, it's called MMPF3, which shows the highest conversion. So, and the explanation is that the cavities are kind of pre-organized for the catalysis because here each cavity possesses 12 cobalt centers oriented toward the center of the cage. So in that case, the catalytic activity is somehow more stimulated than in other two cases. About post-synthetic modification, we'd like to talk too. And so let's have one example. We take the ligand, which we have seen already. So we modify it first. We introduce an amino group, and then proceed in a usual way. So we mix it with nickel. It is microwave-assisted reaction synthesis. We obtain a compound, a MOF, which is perfect MOF as expected. It has a cubic symmetry. But we modify, since we have an amino group which is reactive, we modify it with the mercaptoacetic acid at room temperature. It is easily proceeds, and then modify more. We metallate the sulfur with silver ion. So in that way, we obtain metallated MOF. Here, the ratio between silver and nickel ions is 1:4. And we also check what is the property of this MOF. Initial unsubstituted MOF is known to absorb very well CO2. So CO2 capture properties are shown here. Even the aminated, yes, with amino group, the MOF also shows very good capture properties. The MOF with the silver atoms inside, a bit worse in that case, but nonetheless, it still absorbs CO2. And since we have silver inside, so we can check maybe it can absorb acetylene. Yes, easily it absorbs, and pretty a lot. So we have a compound which can absorb CO2 and acetylenes. Let's check the catalytic activity of this material, since it reacts with both, or at least can bring both together in a in a limited space of the MOF cavities. So it works perfectly. It works perfectly as a catalyst. It catalyzes cyclic carboxylation of propargyl amines with CO2. So useful compounds can be obtained. Let's check another application, that's MOF water harvesting. That's a very interesting topic, appeared relatively recently. It addresses a problem which appears due to the climate warming. Due to the climate warming, freshwater necessities are expected to increase, and at a quite faster pace. And we will face a severe shortfall in next decades. However, the planet does not lack water. It is either too salty, so we see it in seas or in oceans, or it is located in ice. Desalination process can produce relatively cheap fresh water, but requires quite developed distribution infrastructure and large capital costs. But we are interested, will be interested very much in production of the water locally, where it is currently needed. And here, Earth's atmosphere can be the source of the water. The Earth's atmosphere contains large quantities of water in the gaseous form. It is equivalent to 10% of all freshwater resources. So this can potentially be used to address the global problem of water. The question: what techniques can be used to get water from air? And there are already several solutions. That's the fog collection by means of large nets. So-called fog catchers can catch small drops of water suspended in air, coalesce them in larger drops, and which the drops drip down by the gravity to the collection vessel. This technique is widely used in foggy regions, for example, I guess in Great Britain, maybe, or in some mountain regions where, for example, in the morning, the fog can be observed, can be experienced. So the water is collected, and in this way, up to 10% of moisture from air can be captured in the form of drinking or more or less potable water. But let's have a look on a map. That's humidity distribution by regions. We see that the problem of the humidity, low humidity, is actually is very close to, maybe it's even closer than we can think. For example, Africa is very dry region, but it's also Middle and Near East. You see that in the USA, the part is also deserts are located there, so it's quite dry. And even in Europe, in Spain, the central part is desert-like. There are no rivers, and the humidity is very low. So we can use another process to gain water there by cooling. For example, we just have a look on the. Let's have a look on the isotherms. So we have humidity. No, that's not isotherm. That a plot which shows the dew point, that describes where we can get the dew point if we have some humidity of the air, and connects the humidity and the temperature. So let's say we are at 30 degrees. We want to get air out of there. We have to cool down the air by almost 26 centigrades down to 4 Kelvin, and in that way we will reach the dew point and will get the drops of water, condensed water. Okay, but this is quite a problem. So we have to somehow cool the system quite a lot. Let's imagine we somehow can enrich air by water, and let's say we make it. We jump to the curve which describe air is 90% of water. In this case, we need just to cool down by a few degrees, by 4 degrees, and we will get the water condensation. And this is where the MOF chemistry can help. So what we need? We need a MOF material which can absorb water at relatively low humidity, for example, 10%. So just in a desert, at a desert level of humidity. And then release this water with a minimum energy input, for example, by little heating. Okay, so if we have an isotherm of this absorption, we, let's say, describe the system state by the blue one, by the blue curve. So we have saturation at 10%, a bit more, then we get to the saturated state, and then we increase the temperature in this saturated state of the MOF, and in that way we could release water, absorb it, and then if we have a condenser, then we will get this water in the liquid state. And here this plot described this process. And indeed, that was a publication in Science. The MOF 801 displays, exhibit these properties. So it absorbs water at about 10% relative humidity at 25 degrees, goes not to the saturation, but it absorbs quite readily at this relative humidity. And then if the MOF is heated up, then the water is released. Can we improve somehow this absorption? Yes, of course. We should turn to organic chemistry and prepare a new ligand and think about the interaction of water with the ligand. So we introduce oxygen atoms to promote hydrogen bonding. And if we mix this ligand with cobalt, we can obtain a MOF which has channels which readily absorb water at 25 degrees and at any other, and in a very hungry way. So this is again the same plot. During the night, for example, when the temperature is 15 degrees, it can absorb water at a relative humidity 5%. It can absorb, it can be saturated, and then when it's heated up during the day by the sunlight, it releases 82% of the weight of the final system absorbed in absorbed state. So that's pretty a lot. And let's have a look. Once more, we have this here plot, and okay, we make a chamber. This is just a real case study. We have a chamber with this loaded with MOF and with heaters. This MOF is saturated during the day, during the night, up to the saturation point. During the day, it releases water due to the heating. It releases, and all the water goes to the condenser. It was demonstrated that in this way, up to 5 liters of water can be produced using just 200 grams of the MOF. That's the images of the installation, and the experiment was done in the Mojave Desert in the USA, where exactly the humidity is very low, but nonetheless the device could produce pretty a lot of water in this way. Okay, so just a few words about covalent organic frameworks. All the principles applied to the MOFs can be applied also to COFs, but the difference is that instead of the interactions between carboxylic acid and let's say carboxylic acid and metal ion, just organic reactions, organic interactions are used. For example, condensation, very simple reaction. It proceeds smoothly. Another one, obtaining of the phenazine COFs, also the same. Reaction of 2 phenylacetonitrile derivatives with benzaldehyde derivatives, no problem. It proceeds smoothly. The only, let's say, complexity, the only obstacle in this case, that's the conditions which should be very well optimized to get the material in crystalline form. Okay, so let's talk about future perspectives. So to conclude, MOFs and COFs are exceptionally tailorable properties, tailorable materials with customizable properties, application, and so on. but the vast diversity also turns MOFs and COFs into haystack. So making it challenging sometimes for researchers to find the needle when they try to identify the best material. To address this problem, new approaches should be applied. That's first of all, that's automatic synthesis when just screening is made. When many ligands are checked, many metals are checked together, and then the best one is selected out of the checked array. Also, artificial intellect or machine learning should be used, and also high throughput computational screening, just to identify the best system in silico, not in the laboratory, not in situ, but just in front of the monitor, and then check the properties in laboratory. This, of course, would help to develop more this field. Just a few slides, a number of publications, the activity in the field. It's very active. The field is very active, both fields, but clearly MOFs, because of the ease of the synthetic routes, are much more active. Last year, there appeared 14,000 of publications, and we see that there is a constant growth of the publications. More and more groups are involved in this topic, research topic, and more publications appear, more and more subtopics are addressed. At the end, I want to draw your attention that there is a collection of linkers which can be found on the store of the company. Just go to the web page of the store. Under material science, you will find two subsections, that MOF linkers, and you can check the linkers, ready linkers for your nice, beautiful science, and also COF linkers. So essentially that's all. Thank you very much for your attention.
Yeah, thank you everyone. Yeah, I hope you found more about the MOFs and where to find them at Enamine store. And now I would like to take the questions, if any. Yeah. So yeah, before our participants type the questions, I have a few questions. So one question is about the stability of MOFs. So you mentioned different properties, absorption, etc. So how stable, they?
Yes. So that was the initial problem, the stability of the MOFs, but eventually it was clarified. The reasons of that stability were clarified. So finally, what you have seen as an example, let's say, I guess nobody want to prepare something unstable now, because the principles are very clear. So the principles are like that. You need a carboxylic or any other charged group, part of the organic linker, and you take the charged metal ion. So you utilize very strong ionic interaction between both. In this way, you stabilize the interactions between two building blocks. And another weak point can be organic ligand. It is very clear now that you have to utilize rigid groups, like 6-membered or 5-membered heterocycles, acetylene, for example. These are proven to be very stable. The structures with them do not collapse, but also, let's say, there is limit in the number of the groups you can introduce into the ligand. You cannot infinitely extend the ligand, because finally you arrive to the point that the structure collapses during the synthesis, so you just don't get it, or during the desolvatation process, when you just remove the solvent molecules, which always reside after the synthesis, after the preparation. And in fact, they also kind of stabilize the structure. So if you remove them, this is the salient point. In principle, now it is clear how you have to construct to get a stable compound. So just a bit of research in literature, and you will know which ligand and which metal should be used to get a good result.
Yeah, thanks. And that actually brings me to, to another question. So you mentioned that there are approaches to, to select the right MOFs and the right ligands, including those that kind of use AI or machine learning. Are those based on de novo generated molecules, or they explore some data sets, like, for example, our Enamine real?
This is an interesting question. I guess, first of all, I cannot tell you right now because I haven't checked the literature, but all the literature. But what I've seen, that the people try to introduce the data already known, because there are a lot. I will not tell you which number of MOFs already deposited in the Cambridge structural database, but that tens of thousands right now. There are a lot. So there is a lot of data, experimental data to learn from. So I guess both, in principle, I think that both approaches are used, but the most valuable, I guess, that's to get the real data, because this is the real data. So you probably will get a better result with that. I can also tell you that there were attempts to use ChatGPT to suggest to the researchers what to do, just based on the data already introduced to it by the developers, what to do, how to synthesize a stable MOF. And the results which were reported, that's one of the recent publications from the group of Omar Yagi, one of the founders of this research area. And the results apparently very positive. So even not non-specialized models can help a lot. So this is my question. This is my answer. The existing data, it's waste. It's just enormous. It's already helpful in the synthesis. Everything depends actually on the purpose. So what you want to get. And there are many applications area right now.
Sorry, thanks, Maxim. What is the reason for MOFs to be so expensive? Is it the cost of linkers?
I guess yes. So if you check the price of the commercial MOFs, for example, of BASF, which are sold on Aldrich, for example, or other sites, other marketplaces, that's quite expensive. But the price, I guess, drops down now because more and more companies enter this field. There are a lot, and I've checked it just because of interest in this topic. I've checked how many companies exist and what they offer. They offer a lot, and I mean the custom synthesis. So they prepare MOFs for some specific purposes, for catalysis, for gas absorption, or maybe some electric batteries applications. So I guess this is the saturation of the market. So the more companies enter the market, the lower is the price. I guess this is the reason. But definitely, of course, the price of the linker should also go into the final price of the MOF. Definitely, the more complicated it, probably the more expensive it should be.
Yeah, thanks. Yeah, the price matters, and remember that we have pretty decent collection of MOF ligands on Enamine store, so don't forget to go and see that molecules that may be of interest for your project. Another question: can we increase the stability by making composites of MOFs, or composite materials?
Do you mean the co-ligands, or what do you mean? Using different ligands, or what kind of composites?
Maybe maybe depositing them on something, Like,
yes, there are. So the researchers, scientists deposit on electrodes, for example, to make sensors for specific compounds. So there are researchers in that field. Do you mean the stability? You mean the stability, increase the stability of the MOFs deposit?
yes,
or
yes.
Well, as I told before, it is defined by the stability of the connection between the building blocks, and also by the stability, by the flexibility of the ligand. So if these two requirements are fulfilled, then I guess there is no problem. On the other hand, there is kind of try and error methods, of course, always. So you can check different ligands and try to find the best one. That's, as I told, this is advantage and also disadvantage. So we need some prediction tools.
Yeah, so for MOFs that are used for, for gas storage or water storage, so what is the, typical number of absorption desorption cycles?
Yes, this is very important thing, because apparently the people, the scientists and the inventors definitely want to commercialize this findings. So it was checked and it was reported. They checked a lot of cycles. I cannot tell you how many exactly, but hundreds of cycles. And apparently there is no decrease in the property. And they understand that they understand this problem. So, and they even describe what could be the problems with that. And it is checked on purpose. The MOF, which is used with that intention for the water harvesting, it is intentionally it is intentionally tested for the stability toward the hydrolysis. And of course, they select those systems which are stable. And in one of those examples, I guess, do you see my screen right now?
Yes, yeah, we can see a screen.
Yes, just a moment. This one for this one, the authors tested the leakage of the cobalt into the end of the ligand into the water just by washing, whether it's stable or not, because there are very sensitive techniques for determination of the metal traces with ppm concentration, and it appeared that the ligand is very stable. There is no leak of the cobalt. So, and in principle, it's not important in this case. It can destroy because we kind of distillate water. So we absorb it from gaseous phase, and then we desorb it back to the gaseous state. So the only surface which touch the water is the surface of the condenser, and that one can be made of the material which is just innocent in that sense completely. So
thank you. There is one question about the selectivity of the absorption of of the gases. So how can we select the moisture due to main gas in air, like nitrogen, oxygen? So yeah, how can we select?
Yes.
What's the mechanism of selectivity for MOFs? Yes.
So that's the structure. Definitely, that's the structure. So and intentionally, it can be done because of the organic part. It is intentionally can be done in such a way that it is more prone to absorb, for example, methane, and do not want to absorb oxygen, for example, from the mixture, or I don't know, CO, and does not want to absorb hydrogen and kind of enrich. So this is just design of the ligand, design of the topology, because this is also important. I can tell you regarding the water absorption. So as I told, it is important to make it somehow, to make the MOF somehow attractive for water, to water be absorbed. So in this case, we have a lot of the oxygens which are just look inside the cavities. So in that way, water can form hydrogen bonds with oxygens. And here, in this case, in case of this ligand, the two oxygens were introduced because, as I understood, the structure was known before for this compound, but just to make it more the increased affinity of the final MOF to the water, the oxygens were introduced, and in that way the MOF became very water friendly, so to say. So it absorbs the water, it absorbs the water, but does not absorb CO2, for example, or like that, or it prefers water. So that's just designed by design and by analysis of the data already accumulated up to now. And that's the massive of the data is huge. So and the new researchers which want to enter to the field can utilize this data and design the MOF they want.
Yeah, thanks. And there is one question about the metals, because those are, very important parts of MOFs, right? That influence the geometry, etc. So are there any established metal libraries or screen strategies for MOFs with non-ideal, like carboxylate linkers?
Well, actually,
Maybe you can
this
teach us something, yeah.
this is a building block constructor. So you can, let's say, if you know the geometry of the building block can be a metal ion. For example, it can be, I don't know, octahedral iron or nickel or zinc. And you take a ligand which I don't know, forms tetra, I don't know, the spiridians on the corners of the molecule. You get you can predict. I mean, it's not necessarily that you will get this MOF, because here maybe could come into play other players. Like, for example, you can get something which is with hydroxy groups instead of the ligand, so they will be just mixed coordination, or you will have some defects in the lattice, and so you will need to optimize the conditions how to get. But in principle, right now everything is more or less clear. So that's the beauty of the field, that you can predict more or less. In principle, following some arithmetic principle, you just take one ligand, you take one brick, another brick, you connect both, one is octahedral, another is square planar. You connect them, and you can imagine more or less what you will get at the end. Here, maybe the problem is that preferable is formation of clusters, because we use oxygen-containing ligands like carboxylic acids, and in this case, you need to create specific conditions for the synthesis. So in this case, you have to account that maybe metal ions will combine in larger entities and larger units like clusters and so on. So this should be also taken into account. But in principle, this all is predictable. So now there are a few geometries not observed, as I told. So they are waiting their discovery. That's actually why I tell that sometimes it doesn't work. But this is a good guide to synthesize what you want.
Thank you. And there is one question about the YouTube channel, where you can find the recording. That's actually Enamine YouTube channel, and you'll receive the link after the webinar. Yeah, so we don't have any other questions. So I would like to thank you, our today's speaker, this really nice presentation and nice overview of the MOFs. And please remember that we have a lot of MOF ligands stored on Enamine store, and they're easily found on the main page. So please go ahead and try them out. And if you have any questions, do not hesitate to contact our sales team. So with that, I would like to thank you, Maxim, one more time. I would like to thank you everyone for joining us today, and I would like to close the webinar for today. Please follow us on LinkedIn for new exciting webinars. Have a good one.